Hey guys, good morning. Today we're going to be talking about the electromagnetic spectrum. Um, and so the electromagnetic spectrum is just a collection of all of the radiation, which is a form of energy that is emitted by stars. Stars aren't the only things that can emit electromagnetic radiation, but since we're talking about astronomy and stars, we're going to focus on the energy that stars emit. Since stars are, of course, spherical, they emit this radiation in all directions. So it's not just coming to the Earth, it's going everywhere. Um, and we can pick up that radiation through various methods. Our bodies are tuned to pick up a certain fraction of that radiation, but other parts of the spectrum need to have special tools and technology in order to collect and measure that radiation. So we're going to kind of go through this and talk about the bits and pieces of the electromagnetic spectrum, what we can see, and what the other forms of the radiation can do to us. Some of it is good and some of it is bad. So let's go ahead and get forward. But before we do that, we need to talk about waves. All of this energy coming from these stars travels in waves. So very similar to the way water can travel in waves. All waves are is a way for energy to travel. So, as we go further into talking specifically about the spectrum, we need to kind of understand some words that you're going to hear me say when it comes to how that radiation changes. First things first is the wavelength. A wavelength of a wave is the distance between two similar parts. So, for example, from this crest to this crest is a wavelength, or from this trough to this trough is a wavelength. So whatever that distance is gives a wave its wavelength. Okay. The height of the wave above the origin line is called the amplitude. Sometimes you might hear this referred to as amps. Um, Cars and some car stereos put amps in their car to make the wave, the radio wave that they're producing, or the sound wave that they're producing, be more intense or louder. Um, so amplitude has to do with the height of the wave, and what those amps in a car do is really just modify um, the amount of energy that's being given off, sorry, by these waves. Two other words, frequency, or one other word, but high frequency and low frequency. A high frequency wave is a wave that cycles very quickly. So let's talk about a cycle really quick. A cycle is one up and one down. So in this wave that you see up here at the top, that's two cycles. Okay, so a cycle of the wave is to go up and then down and come back to the origin line. So in this wave right here, we have two cycles. This wave here, um, again, you can count from one up and back to its starting point would be a cycle. So if this is where the cycle is right here, this would be one cycle, two cycles, three cycles, four cycles, five cycles, six cycles, seven cycles, eight cycles, nine cycles, 10 cycles, 11 and something cycles. And if that happened in a second, right, that would be its frequency. Its frequency would be 11 hertz, Hertz, which we'll talk about in just a second. This is a low frequency wave. This one is only cycling once and maybe one and a half times in that same amount of time. So this would be something we would call a low frequency wave. All right. So what is in the spectrum? So this slide and the next slide will kind of briefly showcase some of the things, some of the forms of energy that are emitted on the electromagnetic spectrum. So starting over here on the left-hand side, moving to the right, notice how the size of the wavelength changes as we move to the right. Notice how the frequency changes as we move to the right. So as the wavelength right here starts to get shorter, okay, the frequency gets higher. So if we go back to here, it says here as wavelength increases, in other words, the distance between the waves, the frequency decreases. So they're inversely related. When the wavelength decreases, the frequency will increase. So here we have, of course, electricity, extremely low frequency. That's what ELF stands for. Very low frequency. That's what VLF stands for. LF is low frequency. So some of this information here, low danger, right? So computers, Wi-Fi, television, radio, frequencies, those are all low frequency waves and almost safe, not completely, depending on how long and the intensity at which you're exposed. Then we get into microwaves. So again, your microwave at home, cell phones work on microwaves, some telescopes work on microwaves or collect microwaves. Then we get into the infrared. This is the part of the spectrum that is the heat. So when you go outside and you feel hot during the summer, that is the infrared radiation that the sun is emitting. We cannot see it, but we can feel it. And then a very small section of it is what we call the visible part of the spectrum. This is the part of the spectrum that we can see with our eyes. Our eyes are tuned to see these frequencies of light, and they include the 7 colors of the rainbow: red, orange, yellow, green, blue, indigo, and violet. Right above that, we get into ultraviolet. So this is where we're getting into some harmful portions, really harmful portions of the spectrum. Ultraviolet light is the form of light that gives us our suntan, but it's also the form of light that can ultimately, if we're exposed in large amounts to it, can give us skin cancer. Then we get into the X-rays. These are very deep penetrating waves that can pass through your body. And so when we pass X-rays through a human body, it's going to hit off of anything that's hard or solid and reflect back and pass through any soft tissue. And so that's how we developed X-rays. 1 or 2 X-rays every once in a while is not going to cause a big problem, but long-term repeated exposure to X-rays can be harmful. And then the last part is the gamma rays. This is the part that's given off by nuclear radiation like plutonium and uranium and stuff. So if you've ever heard of nuclear power plants melting down, this is gamma rays that are being expelled from that meltdown. Okay, so here just another a little bit more colorful, less busy way to represent the electromagnetic spectrum. Again, notice radio and TV, microwave cell phones, heat by infrared. This is the visible part that our eyes can see. Ultraviolet is absorbed by the skin and used in fluorescent tubes. X-rays, again, can pass through our body, and gamma rays as well, used in medicine for killing cancer. So here, I want you to notice how the frequency and the wavelengths of the wave change. So over here in the safer portion of the electromagnetic spectrum, these wavelengths are longer and the frequency is lower. So that's what makes them a little bit more safe. As we get past the visible portion into ultraviolet, X-rays, and gamma rays, the frequency starts to increase, the wave becomes more energetic, and therefore becomes more harmful to us. Okay? All right. So really quick, just to talk about some things that we're all familiar with when it comes to the EM spectrum, and that is radio frequencies. I know with all of the technology and Spotify and YouTube Music and Apple Music and all of these ways that we get our music nowadays, people actually listening to the radio, the numbers of people listening to the radio are going down. But this has some application to what we're talking about. So whenever you tune a radio to a certain station, for example, like 98.5 The Beat here in San Antonio, or 1200 News Radio WAI that carries the Spurs games, those numbers have a meaning, and those meanings are the frequency that that radio station is sending out its wave. So as you sit in your house, as you sit in class, wherever you are, we are constantly being bombarded with all of the radio stations here in San Antonio. Every single wave from every single radio station is entering into your room. The reason that we can't hear it is our ears can't pick up those frequencies. So we need an instrument, a tool, a device to collect those frequencies, analyze them, and then send them back out in a frequency that we as humans can hear. So that's what radio frequencies are. So, for example, 98.5 The Beat operates on 98.5 megahertz. And so, what that means is because FM operates on megahertz, a megahertz is 1 million hertz, and 1 million is how many times the wave goes up and down in a second. 1 hertz is a wave going up and down in one wave in 1 second. So 1 million hertz is the wave going up and down 1 million times in a second. So 98.5 The Beat operates on a frequency where the wave is going up and down and cycling 98,500,000 times per second. That's pretty fast. Okay. Now, AM radio stations operate on kilohertz. So kilohertz are 1,000 hertz. So 1200 WAI is operating on 1200 kilohertz. So that means that they are going at 1200,000. So you do a little math, it comes out to 1,200,000 times per second. That's how fast that wave is going up and down. So again, here's 2 examples of waves. This one has a frequency of 4 hertz because it goes up and down 4 times in 1 second. This wave over here has a frequency of 14 hertz because it goes up and down 14 times in a second. Now, the other part of the spectrum that's important to us, of course, is how we see. And so how we see color is really pretty astonishing. So first of all light, white light, sent from the sun is really a collection of 7 colors that you see in the background here on the slide: red, orange, yellow, green, blue, indigo, and violet. And if we put all of those 7 types of light together, we get white light, which is what we get from the sun. Now, sometimes we go outside after it's raining or while it's raining and we see a rainbow. And what's happening is as that white light passes through those water droplets, the water droplets act like a prism and cause the light to spread out, giving us the visual of what we call a rainbow. Now, how do we see color? Of course, we have rods and cones in the back of our eyes that pick up different frequencies of light. But the cool thing about it is pigment, which is what colors everything. So the color of your shirt, the color of your pants, the color of your cup, the color of your hair, those things are determined by something called a pigment. And a pigment is a chemical. And that pigment absorbs certain frequencies of light and it reflects like a mirror other frequencies of light. So if you want to have something that is green, since today is St. Patrick's Day, then you would use a chemical that absorbs red, orange, yellow, blue, indigo, and violet, but reflects green light so that everybody else can see that it's green. So if you look at those 3 billiard balls down there at the bottom, black light absorbs all frequencies. So black is literally the absence of color. So whenever you have anything that's black, that is absorbing all the frequencies of light. So it's not reflecting any light back to you. And so your eyes pick that up as being black. The white ball on the right, because it's white, it's reflecting all 7 frequencies of light: red, orange, yellow, green, blue, indigo, and violet. And then the red ball has a chemical on it that absorbs all of the colors except for red. So it absorbs orange, yellow, green, blue, indigo, and violet, but it reflects red back to our eyes. And so that's why we see color. So the next time you look at something that is a certain color, You need to understand, just like in the GIF that is over there on the left, as the sunlight hits the apple absorbs all the colors except for red. And as it hits this box, it's absorbing all the colors except for blue. Okay, so that's how we see color. All right, so back to astronomy. So we have these radio telescopes, these big, huge, they look like satellite dishes that pick up all of the different types of radiation that stars and galaxies give us. And so we can develop that information into different images. And so we can see this galaxy, for example, this is the Pinwheel Galaxy, in different forms of radiation. So over here on the left-hand side, you see this is what that galaxy looks like when we're just looking at the radio waves that are emitted from it. This is what the galaxy looks like, excuse me, if we're looking at the infrared. This is what the galaxy looks like to our eyes. This is the optical or visible part of the spectrum. And then this is what that galaxy looks like in ultraviolet, and this is what that galaxy looks like in X-ray. So using X-rays, of course, X-rays is kind of a way that we can see things like neutron stars. Neutron stars give off gamma radiation, so we can tune our telescopes to see things in different frequencies. Again, this is what that galaxy looks like to our eyes, but because we have the technology to see things in different frequencies, we can see what that galaxy looks like in radio waves, infrared, ultraviolet, and X-rays as well. Okay. All right, so this page right here just kind of gives you a summary of each of the different types of waves, what we use them for. So for example, radio waves we use in TVs, MRI machines, but you can't see this, okay? You can't see radio waves. Microwaves, of course, it talks about how we use microwaves in our home, but also how we use it in astronomy as well. Infrared is the heat. So food that you see under a heat lamp, that would be infrared energy. Of course, there's the visible portion, the ultraviolet portion, X-rays, and then the gamma rays, okay? All right, so that's all the information that you should need. Today's assignment is an Ed puzzle. There's a video produced by NASA about the electromagnetic spectrum that you'll need to complete and get turned in. If you have any questions, make sure you let me know. All right, guys, y'all have a great day. See ya.